We're going to shift gears today and start talking about the nucleus of the atom as opposed to the electrons that we now know orbit around the nucleus of the atom. First, before we talk about the nucleus in any kind of detail, we have to learn a notation to describe the composition of a nucleus. We call that isotope notation. Let me first define an isotope. If you've taken chemistry, you know exactly what I'm talking about already. An isotope I define as a version of an element. That's not the real definition. Okay, that's just the way that I define it, a version of an element. The real definition is an element or an atom with the same number of protons but a different number of neutrons. Okay, how do those two definitions gel together? Well, if we have an atom with 6 protons, it's carbon. Okay, carbon could have 6 protons and 6 neutrons. Or it could have 6 protons and 8 neutrons. Or 6 protons and 7 neutrons. Or whatever. Same number of protons, different number of neutrons. Different versions of carbon. Different versions of the same element with different number of neutrons. We define the type of element by how many protons that element has. So carbon will always have 6. Nitrogen will always have 7. Uranium will always have 92 protons, that is. But there are a different number of neutrons depending upon which isotope or which version of the element you have. All right, this isotope notation will help us to describe the composition of that nucleus with the number of protons and number of neutrons in it. X is going to represent the symbol. So for instance, if we have carbon-14, then the symbol would be C for carbon. Where are we going to find that symbol if you don't know it already? Periodic table. You have a periodic table in your data booklet. Never used it before. Now, here, what is it, 10 days before the end of class? Okay, we're going to finally start using our periodic table. Carbon is the letter C. Now, if you look at your data sheet, you'll also find there's 2 numbers there. One is a decimal number. It says 12.01. One is a whole number, and it's smaller. It's 6. The smaller number of the 2 goes at the bottom of isotope notation. This is what we call the atomic number. And it's the number of protons in the nucleus. That is always going to be the same no matter what kind of element, no matter what version of the element we have, no matter what isotope we have. So whether it's carbon-14, carbon-12, carbon-13, whatever the case may be, that number, that bottom number, will always be 6. If it's not 6, we don't have a carbon. Okay, if it's 7, we have nitrogen. If it's 1, we have hydrogen, so on. You want to identify what type of element you have given that atomic number? Find it on your periodic table. Look for the smaller of the 2 numbers. That will be the atomic number. That will be the number of protons. This number up here, given by the letter A, is your mass number. You're not going to find that on your periodic table. You find an average of the mass numbers on your periodic table. Carbon on your periodic table says 12.01, I believe. Okay, that's because carbon-12 is the most common isotope by far of carbon, so a weighted average of all the naturally occurring isotopes of carbon gives us an average of 12.01. We're never, in Physics 30, going to use that number. Never. Okay, we are going to use the mass number of a specific isotope, never the average mass number, all right? So you're looking at your periodic table, you're going to need to recognize the symbols. Not memorize the symbols, but recognize the symbols. You're also going to need to be able to use the smaller of the 2 numbers on the periodic table, never the bigger of the 2 numbers. So that mass number we define as the number of protons plus the number of neutrons. That allows us to find, well, the number of neutrons. For instance, carbon-14 has 6 protons and 14 protons and neutrons. So how many neutrons would we have? 8. Good. Yeah, you want to find the number of protons? Easy. Just look at the atomic number. You want to find the number of neutrons? Well, it's a little bit harder, but still not too bad. You just got to do a little subtraction there. 14 minus 6 is 8. Never, again, that decimal number that appears on your periodic table. always a whole number that would be given to you. Now, this is the most common way we see this written, but we could also see it written like this. Where's the 6? Not listed. Why do you think that we sometimes don't list the 6? Sorry? Well, you don't have to know it, but it's on your periodic table, and it's always the same, right? Because it's always the same, it's okay to leave it off. If we leave off the 14, well then we can't identify that, right? We can identify the 6 by looking at our periodic table, knowing that it's carbon here. Another way that it's sometimes written is this. Carbon 14. Again, the same deal. Okay, we know the atomic number is 6, so we can just check, or at least we can check our periodic table to find that it's 6, so we don't actually need that 6 written down. This is normally the way you see it, though. Okay, I'm going to give you just one quick example, one very quick example, and then we're going to move on and talk about the meat of the lesson today, that is radioactivity here. Let's say it's uranium-235. Uranium-235. Everybody should have the periodic table handy here. How many protons does this uranium-235 have? No. 92. It has 92 protons, yeah. 90, just kidding, it was a good one. Yeah. We have 92 protons. 92 protons. Okay, how many neutrons does uranium-235 have? 143, right. Which is 235 minus 92. Does that make sense? Good? Easy enough, right? You just got to remember that, easy enough. Okay, this is, it's not very common that we see a question, a standalone question like this. It happens from time to time, but usually this is part of a bigger question, like we're describing radioactivity, and we have to use this as a tool to describe radioactivity. But this is critical. Even though you're probably not going to get a standalone question like this, to understand this is critical as we move forward for the next couple of days through radioactivity. Let's talk specifically about radioactivity now. What is radioactivity? Well, it is a spontaneous process. It is a natural process. It is a random process where one nucleus like carbon or like uranium decays into something else. Chemistry, you learn that carbon is always carbon and uranium is always uranium, but well, chemically that's true. Because in chemistry, you talk about the electrons and how they share and whatever. But under certain circumstances, the nucleus can actually change and carbon can become nitrogen, or uranium could become thorium, or some other element could become some other element. It's alchemy, right? It's the conversion of one element into another. But we don't control this. That's the reason we say it's a natural process, it's a random process, it's a spontaneous process, because the only thing that controls it is nature. We have no say over whether it happens, over when it happens, over how often it happens. It just does what it does. It's like you crazy teenagers. We have no control over you. You just do what you do whenever you want, as often as you want. The resulting radiation that comes from this is called ionizing radiation. Ionizing radiation is radiation that can turn atoms into ions. So we're not saying that it releases ions. It releases radiation that can turn atoms into ions. Does that make sense? And what's an ion? An ion is basically a charged atom, right? It can turn atoms into charged atoms or turn atoms into ions. Why is that a big deal? Sometimes it's not, but sometimes it is. Okay, if we happen to be exposed to that, and we happen to have ionizing radiation turning atoms in our body into ions in our body, then that can lead to all kinds of crazy things happening. Chemical reactions that aren't supposed to take place start taking place. And that's really what biology is, right? Biology is really just chemical reactions. Biology is really just applied chemistry. So if you end up getting all these chemical reactions that aren't supposed to take place, taking place, then all of a sudden you start suffering undesirable effects. Like maybe you get a little sick, maybe you get a lot sick, maybe you start bleeding from all kinds of places. Maybe you get cataracts in your eyes, maybe you get cancer. Okay, maybe you have acute radiation poisoning and you die within hours. Okay, maybe you get your genetic mutations in offspring. Okay, this would be particularly an issue with women more so than men. Why would that be the case? Well, because they carry children, yes. Okay, certainly if a pregnant woman was exposed to ionizing radiation, that would be there would be huge issues with that because of the rapidly developing cells that are taking place within the fetus. But the woman, from the time she's born, has all the eggshells she's ever going to have, right? Men don't. Okay, which means that women in that respect would be more susceptible to it than men for reproductive issues, right? All kinds of things taking place that aren't supposed to take place. So generally we want to avoid ionizing radiation. Although, having said that, listen, you're being exposed to ionizing radiation right now, every moment of your life. Having said that, under normal circumstances, our bodies can repair themselves quicker than the damage is being done. So that tends not to be a problem if our bodies can repair themselves quicker than the damage is being done. If the damage is being done quicker than the body can repair itself, that's when we have trouble, right? Does that make sense? All right. We're going to talk about four, but really three types of radioactive or radioactivity reactions. If you take a look at the practice question set or the example question sets that I handed out on the first day of the unit, I've actually got this table there so you don't have to redraw this. You do have to label everything, but you don't have to draw the table itself. The first kind of radiation that we're going to talk about here is called alpha decay. Alpha decay occurs, they got a really big nucleus, and it's big, it's unstable. We'll talk about why it's unstable in a couple minutes here, but it's unstable and it breaks apart. It breaks off a little chunk of the nucleus and kicks it out, kicks it away in an attempt to become more stable. The chunk that breaks off has an isotope notation that looks like this, 4, 2, alpha. That's the symbol for alpha, right? How many protons is in this little alpha particle that breaks off? 2. How many neutrons? 2. 4 minus 2 is 2. 2 protons and 2 neutrons as one chunk is identical in every respect to a helium nucleus. So sometimes you actually see an alpha particle written not as 4,2 alpha, but as 4,2 He. I don't care which one you use. Be prepared to recognize both as being the same thing. An alpha particle that is released is matter. It consists of protons and neutrons. It is matter. Beta negative? Well, the symbol for beta negative, this is a really, really small chunk that comes off the nucleus. And this can happen in big nuclei, it can happen in little nuclei. Okay, in either case, they're unstable. We'll talk about the reason for that in a little bit. But as a result of that instability, it releases a particle that has these characteristics, 0, -1. How many protons in a beta particle? Not -1? What? How many neutrons? Well, there's 0 protons and neutrons. So what does this mean? A beta particle is an electron. it is identical to an electron, and sometimes we see it written 0 minus 1 e as a result of that. Now, this begs the question, how do we get an electron ejected from the nucleus when there are no electrons in the nucleus? We'll talk about that in a couple minutes. For the time being, we're going to identify beta particles or electrons as matter. They have mass, they're matter. Now, beta positive happens in similar circumstances as beta negative, big nuclei, small nuclei. Again, for whatever reason, it's unstable. We'll talk about that reason in a moment. As a result of that instability, it releases something that has the properties that look like this, 0 plus 1 beta. How many protons? No. What does the number 0 on the top mean? There are 0 protons and neutrons. So there are 0 protons here, and there are 0 neutrons. What does the plus 1 mean? This is actually what we call a positron. It is not matter or energy, rather it is, anyone, antimatter. Antimatter is exactly the same as matter in every respect except for one property, and that one property is usually charge. So it has the same mass, it has the same properties in every way positron does as an electron, except for the charge. It is exactly the same as an electron orbiting around the nucleus, except it's positively charged. By the way, when matter and antimatter come together, does anybody want to know what happens when matter and antimatter happen to come together? They annihilate each other. They annihilate, complete annihilation, and we get 100% of that matter and antimatter converted to energy. 100% of it is converted to energy. It would be a tremendous source of energy, right? But the difficulty in harnessing that is what prevents us from doing that. I mean, you think about how we even contain antimatter. Think about that. How do you contain antimatter? Well, that's easy, right? You just get a bunch of antimatter and put it in a container. What's the container made out of? Matter. When matter and antimatter come together, what happens? Annihilation. Okay, you're getting on the right track. Yeah, go ahead. Guys, listen, please.
Don't you need to use like a magnetic flow?
Yeah. Basically, I mean, scientists haven't contained antimatter for a great deal of time. Like, they're into the seconds of being able to contain it now. But obviously, in order to make it some viable source of energy or some viable source of, you can imagine, not just a source of energy to generate electricity, but power or weapons, right? We have to be able to contain it for more than a minute, right? Essentially the way that we would do that likely would be through magnetic fields, because you could have a charged antimatter particle moving through a magnetic field and contain it with that magnetic field, because the magnetic field causes it to be deflected, right? So odds are you'd probably cause it to move in a circle. Gamma, well, that has a symbol 0, 0, means that gamma is not matter or antimatter, rather it's just energy. Specifically, it's electromagnetic radiation. Remember we said in our last unit, we said that gamma radiation was produced as a result of nuclear decay? This is where we're at here, right? Nuclear decay, no protons, no neutrons, no electrons, no positrons. It's just energy, pure energy. Now, why does alpha decay take place? Why does uranium-235, why is it not stable, and why does it release this alpha particle in an attempt to become more stable? Well, it happens if a nucleus has too many protons. That's a little bit misleading. It's not really the number of protons, it's the number of protons relative to the number of neutrons. Does that make sense? You got too many protons compared to the number of neutrons. Now, why is that a problem? Well, there's 3 forces inside the nucleus. Well, there's actually 4 when you include gravity. But gravity would be so ridiculously small because the masses would be so small. Three forces in the nucleus, the four forces, force of gravity, which we don't care about, the weak nuclear force, which in this context we also don't care about, and then there's the strong nuclear force, which attracts everything. Protons attract protons. Protons attract neutrons. Neutrons attract neutrons by the strong nuclear force. Okay, that's an attractive force, and that's the force that tries to keep the nucleus together, attract everything together. But there's also the electric force, the electrostatic force, that repels protons. The neutrons aren't attracted because, remember we said charged objects are attracted to neutral objects. Neutrons are not attracted electrically to protons. So the electric force is repulsive, and the strong nuclear force is attractive. If you have too many protons, the repulsive force, which is the electric force, ends up being bigger than the attractive force, which is our strong nuclear force. If the repulsive force wins, then the nucleus breaks apart. And an alpha particle, this small helium nucleus, ends up breaking off. Now, it's not like the rest of the nucleus is just gone. If you had uranium-235, well, now you've got something that's just slightly smaller than uranium-235, something that has 2 less protons and 2 less neutrons. Too many protons, repulsive force is too big. You break off a chunk in an attempt to make the balance of protons and neutrons better, the ratio of them better. Yep. SN stands for the strong nuclear force. FR stands for force of repulsion. FA stands for the force of attraction. So the electric force is repulsive. The strong nuclear force is attractive between protons and proton, neutron and neutron, proton and neutron. Now, why does beta-negative decay occur? It's not a force thing at all. It's an energy thing. You have too many neutrons, but that doesn't create an imbalance of force. That creates an energetically unfavorable state. Now, this is kind of wacky what happens here. So the nucleus is unstable because of an energy thing. It's just energetically not working. Okay? Sometimes you're in a room with a bunch of people and you're just like, I'm not feeling the energy here. Right? Not stable. I kind of think of this as a club, the nucleus club. I mean, there's 2 members of the nucleus club. Well, 2 kinds of members of the nucleus club. What's one of them? Who's in the nucleus club? Protons are in the nucleus club. Who else in the nucleus club? Neutrons. They get along famously. They like each other lots. It's like they chat with each other every day. Everything's great. And then one day in the nucleus club, they're meeting 3rd Tuesday of every month. They get together and they say, you know what? The energy's just not working here. We got too many neutrons. We got too many neutrons. The energy just isn't working for us. So what are we going to do? We go around the table and everybody has their ideas, and most of them are stupid. So finally somebody says, you know what? I got a great idea. We don't want to get rid of any neutrons because we like the neutrons, right? We just have too many of them. Here's what we're going to do. We're going to take a neutron and we're going to change it. We're going to change a neutron into, nope, well, kind of. What is it? Again, a proton. We got too many neutrons compared to the number of protons. Let's change a neutron into a proton. That fixes the ratio, right? That makes us energetically more favorable. Oh, but it violates a fundamental law of physics called the law of conservation of, nope, charge. Neutral became positive. So what else happens here? Well, we got to produce an electron as well. But wait a sec, the electrons aren't part of the club. So we kick them out. That's your beta particle. A neutron is changed into a proton and an electron in order to keep the law of conservation of charge working for us here. Proton stays there because, hey, they're welcome in the nucleus club. The electron isn't welcome in the nucleus club. They don't get along at all, so they get kicked out. Okay, we're fine now. We're more energetically stable now. Now, what happens with beta-positive decay? Well, beta-positive decay, you have, once again, too many protons. But it's a different kind of proton issue here. It's not the number of protons causing too much repulsive force. In this case, we're typically talking about small nuclei, or any size nuclei here, small or big. In this case, we have too many protons, and it leaves it energetically unstable or unfavorable. So it's the third Tuesday of the month. It's December, just before Christmas. Club's getting together and saying, oh, man, you know, we've had a good year, but things just, I don't know if it's just a silly season here, Christmas and stress of crowds at the mall or what it is, but things just aren't working for us here right now. I think we have too many protons. So what are we going to do? Let's take a proton and let's not get rid of the proton because we like them, but let's just change them into a neutron. We like neutrons and protons. It doesn't really matter what we got. This makes it more energetically favorable, but I got a problem because it violates conservation of charge. We got positive and then we got neutral, right? Well, we can't just do that. It's a good idea, but we can't just violate the law of conservation of charge. So what do? We get a positron. Well, wait a sec. Positrons aren't part of the nucleus. They don't belong in the club. So what do? Kick it out. We don't want to kick out protons and neutrons. We like them. But we have no problem kicking out electrons and positrons. All right, gamma. Well, gamma is just kind of like a byproduct. It happens as a result of something else. So something else is taking place. Beta-negative decay has taken place, let's say, and the nucleus, as a result of that, is left in an excited state. Well, think about that. You just watched a neutron get changed into a proton and an electron, and then the club kicked out this electron. You'd be excited too. The nucleus is left in an excited state as a result of this, but the nucleus doesn't want to be in an excited state. So it has to go back down to its normal state, and as it does that, it gives off a photon, a gamma ray, an energy, right? It gives off energy to get back down to its, okay, things are okay now. Get back down to its normal state. So it happens as a result of something else already having happened. Does that make sense? Okay, beta decay, some other nuclear process has taken place. Nucleus is left excited, gives off a gamma ray to bring it back down to its normal state. Now, just before the bell here, we've got about 4 minutes, which is about perfect amount of time. We're going to talk about two properties of each of these types of ionizing radiation. They're all ionizing radiation. They all have the ability to change atoms into ions. They all have the ability to damage cells, healthy cells, as a result of their ionizing properties. We're going to rank them in terms of their ability to penetrate matter, to go through matter, and in terms of their ability to ionize matter, to turn atoms into ions. The penetrating power of alpha particles is very low. That's good news for us. It's very low. If you get upset at me someday, and you go home and you say, man, I am so mad. I didn't want to have that test on Friday, that electricity and magnetism response test on Friday, June 1st. I'm gonna get my alpha gun, my alpha particle gun, and I'm gonna come in there and I'm gonna bombard Mr. Dickie with alpha particles. I'm gonna say, bring it on. Because all I gotta do to protect myself from alpha particles, in fact, I'm probably already protected because I'm dressed. Okay? All I gotta do though, beyond that, is hold up a piece of paper, and that'll shield me from an alpha particle. Because the penetrating power for alpha particles is very, very low. I'll just wear my beekeeper's outfit that keeps me completely covered, and I'll be protected from alpha particles. No problem. It's very, very low. Now, gamma rays that are pure energy have a penetrating power that is very, very high. It can penetrate right through the human body. It can even penetrate through several centimeters of lead or concrete. That's why cancer treatment rooms use gamma radiation, and cancer treatment rooms have very thick concrete walls to protect people outside those rooms from gamma rays. Okay? Now, beta, negative, or positive have a penetrating power somewhere in the middle. Okay? We'll say medium. It can penetrate a couple centimeters of flesh, potentially. Now, what about their ability to ionize matter? Well, the good news is, although gamma rays have an incredibly high ability to get through matter, to penetrate matter, they have a low ability to ionize matter. Now, that's not to suggest that they're safe. They are not. They can ionize matter, and they will ionize matter, but they have far lower ability to ionize matter than do alpha particles. Alpha particles have a very high ability to ionize matter. And beta particles, well, they're kind of the fence sitters. Like, they're like, yeah, we can kind of go through matter, but kind of not. We can kind of ionize matter. We can kind of not. We get through more than alpha particles, but not as much as gamma. We can ionize more than gamma, but not as much as alpha. We're the ones that can't really decide what we want to be. We're the ones with the identity crisis. You'd have an identity crisis too if you kept getting kicked out of the club, right?
Yeah.
Right?
I call it revolution.